Hi, hello everyone. In today's class, we will discuss what is a subgraph of a graph, what does it mean by a connected graph, what is a component, what is n-connectedness of a graph, Hamiltonian path and Euler path, Hamiltonian cycle and Euler cycle. All these things we'll discuss in today's class. And this Hamiltonian cycle is a very interesting problem. We will see why that problem has got such a prominence. Okay, first let us discuss what is a subgraph of a graph. If you are given a graph represented by v comma e, then you take any subset of the vertex set and you take any subset of the edge set of the original graph that we are considering. Then this particular tuple, that is w comma f, constitute the subgraph. Here what I am assuming is all the vertices that are part of the edges in f, those vertices are there in the subset w, that is in the subset w. What I mean is that whatever edges that I want them to be part of subgraph, the vertices constituting of these edges will also be there in the vertex set of the subgraph. If G v comma E is a graph, then you consider a vertex subset and an edge subset and put this property that all vertices of the edge set are there in the vertex set W, then this particular thing is called a subgraph of the original graph. Here in this example, this is the original graph, and what I am constructing this particular subgraph. What is the vertex set? I am taking possibly all the vertices except this guy. This guy I am not taking him. All other vertices are there. Hence the vertex set of H is a subset of the original set, subset of the vertex set of G, and I am considering few edges of G. For example, this is there, this is here, and this is here also, this is here and this is here also, and say this particular edge I am not considering here. Like that I will take a subset of this guy, and the resultant structure is called a subgraph of G. Very meaningfully it is a subgraph because both vertex set and edge set of the subgraph are subsets of the original vertex set and edge set. And if you have got two distinct graphs, say G1 and V1 G2, then you can union these two graphs and you can get a graph, you can get a resultant graph which is called union of these two graphs. How do you do it is you just take vertex sets of two graphs G1 and G2, just union them, and then take edge sets of the two graphs, that is E1 and E2, and union them, and the resultant structure is called union graph of G1 and G2 represented by G1 union G2. Let us see if these are the two graphs that we have got. Say if this is G1 and if this is G2, then let us see what is the union of these graphs. Here there are some graphs which are in common actually between G1 and G2. For example, A is common here and it is here, B is here and B is here, F is here but F is not here, E is here and E is not here. Now let us see what is the union. How does the union looks like? If you actually union it, it will be like this. All the edges that are there in between in both of the graphs will remain, and the edges that are there in the graph 1 will also come which are not there in the graph 2, and vice versa. For example, DE is here but not here, but in the resultant graph this particular edge will come. BF is here but not there in this graph, in the resultant graph we will get BF, and all other graphs which are in common definitely they will come anyway. So the resultant union of these graphs will be looking like this. Now let us see how we can represent a graph so that we can manipulate it, we can do some operations on it. How a graph can be represented, definitely it can be modeled very nicely in a webby looking way, but if you have to represent it in inside a computer or in a data structure, how are we going to represent it so that we can manipulate on these graphs nicely? There are a couple of ways that you can represent a graph. First one is adjacency list and the other is adjacency matrix. Adjacency list is very simple. What it says is, say if you have got a graph like this, probably you have a table or a list in which you just mention all vertices, how many vertices that graph is having, you just put them there. Here there are A, B, C, D, E, F, 6 vertices are there. So you put all these 6 vertices in this particular table, then you will have one more column in this table called adjacent vertices. For A, whatever the adjacent vertices are there, you just write them here. For A here in this graph, it has got 2 adjacent vertices, that is B and C. So you just write B and C over here. And what are the adjacent vertices of B? B adjacent vertices are A, C, F and E. So just write them. So this is this kind of representation. Definitely you can represent it in a list if you got introduced to data structures and all. So basically this particular structure, that is graph, can be represented nicely like a list or a table. If you go into more depth of program languages, you have got a lot of data structures that you can represent this particular table. So one of the nice ways of representing a graph for easy manipulations is adjacency list. This is called adjacency list. And directed adjacency lists are nothing but when you have got, say you have got an example like this. Here you write vertices and here you write adjacent vertices. Say for example A, what is the adjacent vertex for A? For this directed graph, just list the terminal nodes of A. What are the terminal nodes of A? B is one terminal node, D is another terminal node. So write only them. F is not terminal node. In fact, this particular edge, there is this particular edge is coming on to A, is coming into A. They are not going away from A. Only these two edges are going away from A, and when these two edges are going where they are being terminated, that particular vertex you need to write here. So BD are the adjacent vertices for the vertex A. Say for example for B, what is the adjacent vertex? absolutely there is no adjacent vertex that B has got. It is from B, there is no edge that is going away from B, so it is null. It is null. For F, what are the adjacent vertices? A, C and E, because because there is an edge from F to A, F to C and F to E. The adjacent vertices for F are this. So basically what I mean is listing terminal nodes of each edge incident from that node is what you write here. All terminal nodes of the edges which have got starting edge as A, that's what you write here. That is how you maintain this directed adjacency list. And these adjacency matrices, let us take a simple graph like this. So how do you represent a graph by this adjacency matrix? Is very simple. You just think of a matrix, put all the rows as the vertices, say these are all A, B, C, D, E. You put them here A, B, C, D, E, and put the columns also the same way, same nodes, that whatever you have got, write it. Now do one thing. If there is an edge from A to E, then go from A to E here, put 1. If there is no edge from A to E, put 0 there. For example, A to C, there is no edge, so put 0 over here. A to D, there is an edge from A to D, so put 1 over here. So A to B, there is an edge, so put 1 over here. A to A, of course it is 0. So basically take two vertices, if there is an edge between them, then put 1 in the corresponding place of the matrix, that is C and E are having an edge, so go from C to E here, put 1 over here, otherwise put 0. Basically what I am saying is put if you are going to call this matrix Aij 1 if there is a edge between the vertex Vi and Vj, otherwise put 0. This is how you can nicely represent a matrix, a graph, by making use of matrix. Now just look at this particular thing. If we have the simple question, that is how many simple labeled graphs, basically simple graphs, that means no loops or no parallel edges between any two edges. If you have got n vertices, how many graphs are possible on n vertices? That is the question that is being asked. Your vertex set is V1, V2, so on Vn. Then we all know there are quite number of edges, there are quite number of graphs that you can talk on the base set V, on the vertex set V. The question being asked, how many number of possible graphs could be there on this vertex set V? For that I'll ask another question. How many possible graphs, how many possible edges are possible in on vertex set V? If V is given as V1, V2, Vn, how many possible edges could be there? I say n choose 2, because you take you choose any two vertices from here that corresponds to an edge, isn't it? You take any two subset of this vertex set that will give you a tuple which is nothing but an edge. So how many possible subsets are there on this particular vertex set? I say n choose 2, obviously, because there are n elements. I am choosing 2 elements at a point of time. There will be n choose 2 subsets having size 2. That means that n choose 2 possible edges are possible on this vertex set. Okay. Now let us see some basic mathematics. If we have got a set of k elements, say that set B A is equal to A1, A2, so on AK. How many number of subsets will be there for A? You know what a subset is. You take some elements from A and that constitute a subset. For example, A1 is a subset of A, A1, A3 is a subset of A, empty set is a subset of A, A2, A4, A6 is a subset of A. What I am asking here is how many possible subsets, how many subsets are there on the set A? So very basic mathematics tells us there will be 2 power k subsets will be there on set A. So it is very simple. How many, to compute this, how many subsets of 0 cardinality will be possible? Only one, that is empty set. How many subsets of cardinality to 2 are possible? K choose 2. How many subsets of cardinality 3 are possible? K choose 3. How many subsets of cardinality k are possible? K choose k. Just add these guys up, then you get 2 power k. 1 plus k choose 1 plus k choose 2 plus k choose k. Here this is how it is coming, 1, k choose 0. What I am saying over here is how many number of subsets of A are possible with cardinality 0, k choose 0. How many subsets of cardinality 1 are possible? K choose 1. How many subsets of cardinality 2 are possible? K choose 2. Similarly with k with how many subsets of k cardinality are possible? It is k choose k. Just when you add all these guys up, you get total number of subsets, isn't it? And our intermediate mathematics will help us to say that this is equal to 2 power k, just because 2 power k you can write as 1 plus 1 whole power k. When you do this binomial expansion, you get this guy out here. Hence this whole sum is nothing but 2 power k. Now what we have established is, if I have got a set containing k elements, how many number of subsets will be there of this set A? The answer will be 2 power k, isn't it? Answer will be 2 power k. That is what we have established now. Now we go back to our original problem. We said that if I have got a set V having say n vertices, then we concluded that there will be n choose 2 possible edges are there on this vertex set. Now I call this, say all the possible edges by this particular symbol, say F. F is set of all possible edges on V. Anything can afford to be an edge of a graph. if that is the case, then I have got, so each subset of this F together with this vertex set, will it not give a graph or not? You take the vertex set V and you take some subset of F, that means some possible edges you take, you will get a graph or not? Definitely get a graph, isn't it? So the number of possible graphs is nothing but how many number of subsets are there for F. If I know the number of subsets of F, I know how many graphs are going to be there on V. Now how many subsets of F are there, and we know that F is containing n choose 2 elements or edges. F is containing n choose 2 edges. Then how many subsets are possible? How many subsets could be there on F? Just by the lemma that we have proved here, 2 power n choose 2 subsets are possible on the set F. Each subset will give you a graph. So 2 power n choose 2 graphs could be possible on the vertex set V. Okay. Now let us see what an isomorph, when do we say two graphs are isomorphic? Let us we'll see formal definition within some time, but informally speaking, I'll say two graphs are isomorphic if and only if the structure remains the same except how you are going to call the vertices, except the vertices are being called with different name in the other graph. There is no structural difference between these two graphs. Then that is what, then actually these two graphs are equivalent, accepting the fact that the vertices are called with different names. Formally speaking, if you have to define it formally, if you have got a graph G1 and another graph G2, then if you can define a bijection from V1 to V2, such that V1, such that if A and B are adjacent in V1, then if and only if f of A, the corresponding vertices in V2 also should be adjacent. I will come back on this. What I am saying is, I got two graphs G1 and G2. I say they are isomorphic if I am able to find a bijection. What is a bijection? When I say bijection from V1 to V2, that means I should be able to define a function f from V1 to V2, and that function f should be 1 1, that is injunction, and f should be onto as well. When f is 1 1 and onto, then we say the function f is bijection. That this is what we have seen in our functions class, isn't it? So when I have for two graphs to be isomorphic, I should be able to cook up a function such that it is bijection from V1 to V2. And what do you mean by bijection? That means if A is a vertex in V1, then f of A is a vertex in V2. That is what it means by defining a function, isn't it? If I got a function f from V1 to V2, take any element in V1, it should have a corresponding image in V2, isn't it? what does the function do? It takes an element from V1 and it gives an image of that particular element in V2. I am taking, when I take an element, I take a vertex in vertex A in V1, f of A will be in V2 definitely, and it is going to be another vertex definitely. Okay, and the f should be like, if I know A comma B are adjacent in V1, that means you got a graph G1 and graph G2, isn't it? This, you take two vertices from graph G1, A and B. If A and B are adjacent in graph 1, then the images of A and B under the function f, that is f of A comma f of B, should also be adjacent in V2. When this is happening, this should be happening, and vice versa. When I can cook up a function such that it is bijection from V1 to V2, and whenever two vertices in V1 in G1 are adjacent, the corresponding images under the function f should also be adjacent, and vice versa should be happening. When this particular whole condition is happening, and if you are able to define a function f such that these guys are being satisfied, then I say G1 and G2 are isomorphic, otherwise not. So given two graphs, if anybody asks you to find out they are isomorphic or not, you have to find a function which is bijection, and if two vertices are adjacent in G1, the corresponding images under the function f should also be adjacent, and vice versa should be happening. Then we say these two graphs are isomorphic. Let us see an example, and we will see some necessary conditions for two graphs to be isomorphic. First condition will be the number of vertices in V1 and number of vertices in V2 should be the same, otherwise they cannot be isomorphic. Of course, if you have got a graph like this, say this is a graph of 4 vertices, and you have got a graph like this which is a graph of 3 vertices, they cannot be isomorphic, isn't it? That means it is not just names that are mattering here. Say the names of these vertices are A, B, C, D, and the names of these vertices are 1, 2, 3. It is not just the names are mattered here, the structure itself is changed from this graph to this graph. The structure here is there are 4 vertices, and here there are only 3 vertices are there. The structure of the graph itself is different, hence they cannot afford to be isomorphic. So first necessary condition is the number of vertices and number of edges in both the graphs should be the same. Another condition is, say in graph G1, if you have got 3 vertices of degree 4 are there, suppose, then the graph G2 also should have 3 vertices of degree 4, otherwise it is not isomorphic. It's quite intuitive, isn't it? When I say graph 1 are having 3 vertices of degree 4, then graph 2 should also have 3 vertices of degree 4, otherwise what is going to happen is G1 and G2 will be structurally different. It is not just name change that is differing G1 and G2, it is structural change that is differing them. hence they cannot afford to be isomorphic. The number of vertices with degree n is same in both the graphs. Number of vertices of degree 4 for that matter should be same in both the graphs, otherwise they will be structurally different, isn't it? And then for every proper subgraph of one graph, say you got G1, you know what a subgraph is. Say if this is the subgraph of H1, proper subgraph means it is properly contained in G1. That means that H1 is actually not G1. H1 is something less than G1. At least one edge is going to be in G1 but not in H1. That is what is proper subset. We have seen it, what is proper subset. What is a proper subgraph is at least one edge of G is not going to be there in H1. You have got one subgraph, proper subgraph of G1, then you should be able to find another proper subgraph H2 such that there is a isomorphic between these two subgraphs. Then also this should be happening, otherwise we can't. We can directly say that the structure of these two graphs is different, hence they cannot afford to be isomorphic. So for two graphs to be isomorphic, if you have got a proper subgraph H1 of G1 and if you are not able to find another subgraph H2 which can be isomorphic to H1, then the graphs that we have got G1 and G2 cannot afford to be isomorphic. If the number of vertices in graph 1 and graph 2 are different, then they cannot afford to be isomorphic. All these properties is what we have seen. We will see with an example how we will decide isomorphism between two graphs. One most important thing is the two graphs may look like altogether different when you actually draw them, but they may not be really distinct by the very nature of their structure. They may be equal, but they can be drawn very much differently. So the knack is to find out how we can nicely map the nodes of these two graphs so that the structure remains the same. Let us see here, this is one graph and this is one graph. Let us spend some time whether these two graphs are isomorphic or not. Say each guy may have some names, it does not matter, but if you are able to find the structure, it is fine. So there is actually, imagine there are some names over here, maybe alpha, beta, gamma, delta and all. I am not putting those names for these vertices, but now I am going to give the same names that are there so that the structure remains the same. Suppose if I call this D and this call F and this guy call B and this guy A, this guy E and this guy C, then actually this graph is nothing but this graph, isn't it? So B, for example, B is having edges from B to A, B to D and B to C. Here also it is having edges from B to A, B to D, B to C. F is having an edge from, there is an edge that is from F to E and F to C. Here also there is an edge from F to E and F to C. There is an edge from A to B and an edge from A to E, edge from A to B, A to E and A to D. A to D also is an edge, there is an edge. So actually, by naming nicely, these two graphs are actually the same, though they are looking different. Now let us see whether these two graphs are isomorphic or not. So here, to check whether they are isomorphic or not, first we will see the sufficient conditions. If the number of edges here and the number of edges if the number of vertices here and number of vertices here are different, then I can straight away say that they are not isomorphic. Here how many vertices are there? Say 1 2 3 4 5. Here how many vertices are there? 1 2 3 4 5. So that is being satisfied. So it can be an isomorphic, there can be an isomorphism between these two graphs. And let us see the number of edges: 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. The number of edges are also the same. So there can be a possibility of both being isomorphic. So what I mean here is, I am just checking these conditions. I have checked this condition first. If this itself is not satisfied, I can straight away say they are not isomorphic. If this is satisfied, then I will check the second property. What is the second property? Same number of, given n, there should be same number of vertices with a degree n in both the graphs. So the first property of the first property of having the same number of vertices is being satisfied. Second property, first property means another thing, what it says is same number of edges, this is being satisfied. Let us see the third property, that is different number of, there should be same number of edges with degree n in both the graphs. Now let us look at degree 2. How many vertices are there in this graph with degree 2? This guy is having degree 3, this guy is having degree 3, this guy is having degree 3, this guy is having degree 3. So only D is the only guy who is having degree 2. Hence the number of vertices in this graph who are having degree 2 is 1. Only one guy is having degree 2. And let us look at here, this guy is having degree 2 and this guy is having degree 2 and this guy is having degree 2. Of course this and this is not having degree 2. In this graph there are 3 guys who are having the same number of, who are having the same degree. This guy, in this graph there is only one guy, in this graph there are 3 guys who are having degree 2, which is not correct. If this is being satisfied, we can straight away say that these graphs are not isomorphic. Hence we conclude that without any further study, these two graphs are not isomorphic. I would like to drive one point over here. Here fortunately for us, the second property has not been satisfied, so I am able to say that they are not isomorphic. Say if it is being satisfied, and the third property of every proper subgraph of graph G1, for every proper subgraph of G1 there is a proper graph of G2 such that these two subgraphs are isomorphic. Suppose this condition is there for us to see, we will check that. If we fail here, then also we can say the two graphs are not isomorphic. Suppose this particular condition is also satisfied, then can we say that two graphs are isomorphic? No, we can't say. You have to find other ways of proving the isomorphism. They are only sufficient conditions. They are in fact necessary conditions for two graphs to be isomorphic, but they are not sufficient. Just because two subgraphs are satisfying these three properties, you cannot say that these two graphs are isomorphic. What we can only say is that if any of these property is not being satisfied, then these two graphs are not isomorphic. This is only what we can say. That's, I hope you understand what does it mean by necessary and what does it mean by sufficient. Now let us see what is a connected graph, or when do you say two vertices in a graph are connected. So a path of length n from u to v is a sequence of adjacent edges going from vertex u to v. What this means is, so if I have got this particular graph, what I am saying is path from u to v, one of the path from u to v is this sequence of adjacent edges that is starting from u and finally reaching v. Then I say there is a path from u to v, and I travel like this and finally I go like this. When I reach this is what I call, this is a path from u to u, and this particular path of starting from u and going through some of the vertices and traveling through the sequence of adjacent edges and reaching back to the vertex u, this particular path is called a circuit. Actually, path traverses the vertices along it. Definitely when you go this, you traverse through this particular vertex, you traverse through this vertex, this vertex, this vertex, this vertex, this vertex and this vertex. And we say a path is simple if it contains no vertex more than once. What does it mean? Suppose you take this particular example. I say this is u and this is v, and I say this one, say v1, v2, v3, v3, v4, v5 and say v6. There are other edges. Then u from u to v1, v1 to v2 and v2 to v. This is a path from u to v. There is absolutely no doubt about it, isn't it? And I say another path, that is from u to v1, v1 to v2, v2 to v3, v3 to v4, v4 to v5, v5 to v5 to v2. This is v2, isn't it? This is v2. This guy is v2. So u to v1, v1 to v2, v2 to v3, v3 to v4, v4 to v5, v5 to v2 and v2 to v. This is also a path from u to v, isn't it? This one, this and this. This is also a path. But this is not simple path, because in the path when I write, the path looks like this: u, v1, v2, v3, v4. This is how I am traversing through the vertices, isn't it? v5, v2 and v. v1, V2, V3, V4, V5, V2, V. This is the path, this is another path. This is not simple path because this particular vertex V2 has been appearing more than once, in fact twice in this particular path. It is appearing here as well as here. Hence, this path is not simple. The path that we consider the first go, that is U comma V1 comma V2 V. This is U, V1, V2, V. This is another path, isn't it? This is another path. This path is a simple path because no guy in between or no vertex through which the path is traversing is not being repeated. Hence, this is a simple path. Okay. So basically a path from U to V is nothing but a sequence of adjacent edges going from vertex U to V, and paths in directed graph are the same way, but the only thing is when there is a path, we say path only when there is proper direction, then only we say path. Say if you have got a graph like this, say this is U and this is V. I say there is no path because from here to here I am able to go, but from here to here I am unable to go because there is an arrow from here, there is an edge from V to this guy, V to say V1, but not V1 to V. And similarly when I go here, I am not able to proceed anywhere because for this guy all the edges are coming to it. So there is no path from U to V. You need to take the direction into account when you are talking paths for directed graphs. Now we will take any undirected graph. We call that graph connected if and only if there is a path between every pair of distinct vertices in the graph. What does it mean? I take this particular graph, this is connected because I take any two vertices, any pair of vertices you take, you have a path from one vertex to the other vertex. Hence, this is a connected graph. Whereas you take this particular graph, all this together, is it a graph or not? First of all, this and this together, definitely that is a graph, but is it connected? No, it is not connected because this vertex and say this vertex are not connected. There is no path between this vertex and this vertex, that is U and V. You have got a pair for which there is no path existing in the graph. Hence, this is called disconnected graph. Okay. Now we will see this particular theorem. What it says is there is a simple path between any pair of vertices in a connected undirected graph. It looks so simple, but this particular statement is not so obvious also. We all know that when a graph is connected between any two pair of vertices, there is going to be a path. That is what we get from the definition of connectedness of a graph. There is no problem with it. So given any two vertices, say U comma V in the graph G, then I know there is a path. Absolutely there is no issue. But what here we are supposed to do is there is a simple path between these two vertices. The simpleness is not there in the definition. Definition says only there is a path. but actually we can prove that there is always a simple path. How do we do it? I prove again this particular theorem by contradiction. This contradiction is very powerful. I said when I was dealing with proofs section. By making use of this technique, you can really do wonders. How does this work? We already know. Let us see how it is applicable over here. Now I take, say, two vertices. In fact, we have to prove that between any two vertices there is a simple path. I will take two vertices u comma v in V, where G is equal to V comma E. This is the graph and I have taken two vertices. I have to prove that there is a simple path between U and V. That means that path should not have any vertex getting repeated. How I am going to prove is that definitely because G is connected, that is what is given to us, isn't it? When if G is connected, we have to prove that there is a simple path. Because G is connected, there are going to be n number of paths between U and V. We don't know. There can be one path, there can be two paths, there will be 100 paths. There will be a number of paths. That all we know. Now what I am saying is that because these paths are finitely many, I will take up a path which is having the minimum number of vertices in it. How do you represent a path? Basically, U, V1, V2, V3, so on, Vi, so on, Vj, so on, Vn minus 1, Vn. This is how a path looks like, isn't it? This is your starting vertex and this is your ending vertex. This is your U is the starting vertex, this is ending vertex. There are number of vertices through which your path is traversing through. There is an order here, isn't it? Okay. Of all these paths, what I say is there will be n number of paths between U and V. Say this is Vn and say you can have V over here. This is the starting vertex and this is the final vertex and this is the path. These are the intermittent vertices through which the path from U to V is traversing, and there will be a number of paths. This is one path. Like that, there will be several paths. Of all the paths, I will take the path with the minimum number of intermittent vertices, where the path which is having minimum number of vertices between U and V, that path I will take. Can I take it or not? I will definitely be able to do it because I will write down all the paths that are possible between U and V. They are going to be finitely many because the graph itself is finite. I will write down, and for each path I will count the number of vertices between U and V. Among them, which is having the minimum number of vertices, that path I am taking. Let that path be this. This is the path which is having the minimum number of vertices between U and V. All other paths are having more number of vertices. Okay. If this is what I take, I can definitely take it. I have got all the freedom to do it. Now what I am claiming is, boss, this is the simple path. I just say that. If you say it is not, I will get a contradiction. Hence you have to accept it as the simple path. Simple path as the path which is having minimum number of vertices. Okay, I am saying this is simple path. You say not, it is not simple path. You say, then what does it mean? It is not simple path means there exists a vertex which is being repeated in this sequence, isn't it? in the sequence of V1, V2, Vn, there is a vertex which is being repeated, then only you say it is not simple. Let Vi and Vj are the same and say Vi is being repeated. Vi is here and Vi is here also. Vi is equal to Vj. That is what it means repeated. Two vertices are being repeated means this and these are the same vertices. Vi is being repeated. So when if for all you know, how does this path looks like if I draw actually? If this is Vi, I am going somewhere like this, and finally I am coming here back, that is here Vj, and again I am going here, isn't it? This is V and this is U. When in a path like this, when you get a vertex being repeated means the path is going like this, V1, V2 and say V3, path is going like this, you have reached Vi and you have done something, you traversed through some other vertices and finally you came back to the same vertex because Vj is the same, and then again you traverse through and finally you reach Vn. Okay, you are getting what I am saying? Because Vi and Vj are the same, you will be entering Vi and going through some other vertices and again coming back to Vi, and from then onwards you again start the journey to reach V. This is what must be happening. This is what it means by a vertex here is being repeated, isn't it? So what I say is, boss, instead of taking this as the path, I take this as the path. I take U, V1, V2, V3, so on, Vi and Vj plus 1. This will be Vj plus 1, isn't it? Because Vj is connected to Vj plus 1, Vj plus 1, so on, Vn and V. This path is also a path from U to V, isn't it? It is going like this, from U to V1, V1 to V2, V3 to V2 to V3 and Vi, and instead of going like this as in the original path from Vi, I just go to Vj plus 1, the next element of this Vj, that is Vj plus 1, and I go like this, isn't it? This is also a path, but if you see, definitely length of this path is smaller than length of this path. But when I have started my journey, I said this is the smallest path, there is no other smaller path than this. Now I have got a smaller path than what I have started with. This is a contradiction. This contradiction has arisen due to our assumption that this path is not simple, path. Because we assumed it is not simple path, I got a contradiction that this itself is not the smallest path. Hence, this being not smallest, this being not simple path is not true. Hence, this is the simple path. That is how contradiction works, isn't it? That is how we can prove this particular theorem. So what we have established is, if we have got an undirected graph that is connected, is given to us, then there is always a simple path from vertex U to vertex V. In fact, for all pair of vertices, between all pair of vertices, there is going to be a simple path. That is what we have established. And we say a directed graph strongly connected when there is a path from A to B for any pair of its vertices, given any pair of vertices, if I am able to find a path, that is directed path from A to B, I say the directed graph is strongly connected, and there are edges but without direction. If I can have path from one vertex to another vertex and this is holding good for all vertices, then I say it is weakly connected. The example is if this is U and this is V, actually there is no path, there is no directed path from U to V. Okay, I can say this graph is weakly connected because if I remove the directions to each of these vertices, each of these edges, there is a path from U to V. That is why it is called weakly connected. If this graph is not strongly connected because there is no directed path from U to V, but it is weakly connected because if I erase these directions between each for each edge, then there is a path from U to V. In fact, there is a path from any pair of vertices if I take out the directions of edges. Hence, it is weakly connected. Okay. So, in this class, what we have seen is what is a subgraph of a graph, how we can union two graphs, how two graphs can be isomorphic, how we can define a graph is connected, and we have established finally that if you have got any connected simple graph, if you have got any connected graph, then you can always find a simple path between any two of its vertices. Okay, thank you. Let us meet in the next class. Bye.